Okay, welcome to our third ML tutorial live session. This time we're going to look at the support vector machine, and then with the support vector machine, we will end the big paradigm supervised learning, and then we'll begin the new big paradigm, which is an unsupervised learning with clustering algorithm. And then before that, we're going to look at the PCA, and then we'll go over to the K-means clustering algorithm. So first, let's go to SVM by Kamen. Can you share your screen?
Oh, yep, sharing screen. Should be this one. Can you see me scrolling up and down?
Yes.
Yeah, perfect. Cool. So this notebook was slightly less interactive, so there's going to be less cells to fill in as we go through it. Jake, I'm very happy to hear that you haven't learned the material yet, because it's going to be quite interesting to discuss with you. Sort of your thoughts on the things and whether you've tried any interesting kernels and things like that. But yeah, so this notebook is introducing in general support vector machines. Nick has provided further information in the newest recorded lecture that's going to be uploaded, or has been uploaded already to the YouTube channel. So yeah, just very briefly to go over support vector machines again. They're classifiers that use hyperplanes to separate our data into different classes. So the defaulting, like the default problem here is binary classification, where you have just two classes and you want to separate them. So support vector machines try to find the hyperplane that leaves the widest margin between it and data points of the class, where the margin is the distance between sort of the plane and like based on the orthogonal components of the plane. So like if my plane into D is a line, I want to maximize the distance between the points on each side and the line. Linear support vector machines are quite constrained models, as you can imagine. Like when my data becomes more complicated, as you can see in the example, I need to run things to be able to see things. So this is a thing, but I think this goes. Yeah, like you can't find a line here that would separate things into the two classes correctly. So if that was the only thing that they could do, they wouldn't be a very useful model. However, using what is known as the kernel trick, we can learn nonlinear boundaries. The idea of the kernel trick is to transform our input data into some different representation using feature mappings, and then like the way the support vector machine is set up will only ever take inner like dot products of these feature mappings, and the kernel is exactly dot product of feature mappings. So to cut the long story short, if we define a kernel for the SVM, we don't need to worry about what the feature representations of each data point looks like. We just know that the math works out well. Interesting point to point out here is that these are called support vector machines because the weights in quotations of the support vector are actually linear combinations of the data points that lie on these margins, and these data points are called support vectors. So it's quite interesting that the weights of the model is just a linear combination of the data points that we have. Cool. So let's see what we have to do in this notebook. So we provided some code to sort of generate data on like a grid so that we can produce these nice plots. And we provided the iris dataset, which I think we've seen in previous notebooks. So first, we're given code for a linear SVM, which this is scikit-learn, I believe, yes. which you can just get from scikit-learn. You're given the API to fit the data, and then you can show what the classifier does by taking that grid of points and classifying each of the points with the model. So here we see the linear SVM, like the SVM with the linear kernel. Obviously has a linear decision boundary. Anything on this side is classified as blue, and anything on this side is classified as red. Cool. So that should be clear enough. Then come in the kernels. So I think in this notebook we look at only two kernels: the RBF kernel and polynomial kernel. So in general, a kernel is a function of two arguments that satisfies some conditions. In application, you would rarely try to design your own kernel. You would be more likely to just use existing kernels, and also, as we'll see in a bit, sums of kernels or product of kernels. So here we're going to look first at the RBF kernel, which looks like a Gaussian distribution. If you've seen it, if you haven't seen it, it's just the distance between the 2 points times some hyperparameter, like some scaling. Well, the negative of the distance, I guess, exponentiated. So when we use the kernel, like the RBF kernel, we get a very clearly non-linear boundary here. You can sort of see that you get this closed region, and this is very often the case with RBF kernels. Is you get like contour lines rather than the planes that sort of separate the space into two things, and that may not be a good thing. For example, in the data sets that we're given here, if I had a query point here and I wanted to predict what class it would be, I, like personally as a human, wouldn't feel like it being red would be the correct label. So that's something to be aware of, like the properties of the kernels, which you can gain either by playing around with them a lot in Todo, or actually like sitting down and thinking about how this quantity changes. Like expanding the formula here, you can see how it depends on the two data points that are fed into it. Cool. So that's one of the kernels. The other one is the polynomial kernel, which we have to fill in, which your cheat sheet should look there we go. Should look like this. And why is complaining? What's up? Right, so it's drawing the boundary, but it's not drawing the line, the points.
It's because you've written, scroll up, it says LELDGE colors on the row which starts ax.scatter.
Oh, thank you. Yeah, so got the things. So here you can see that the polynomial kernel seems to be a better fit for this data set, because the things over here are classified with something that's more sensible as the blue class. However, it's not very satisfactory that this line sort of passes like this, right? Like we would expect the line to maybe pass somewhere over here. So maybe the experimenting with like kernel of a different degree could lead us to a better solution. Yeah, like the tool sort of gets a more sensible thing, but misclassifies this. So here you can see that there's like this is a hyperparameter, right? You need to if you want to be like really principled in how you approach this, you need like a validation set on which to pick this hyperparameter. Likewise for the regularization constant C, which is mentioned somewhere here. Did I mention it? Yeah, so you can think of the regularization constant as sort of similar to the L2 regularization constant in linear regression, usually where you're trying to keep down the weights, the magnitude of the weights you have, because you don't want your model to be very complex. This is another hyperparameter that you need like to cross-validate to get the best model we can. So we were given the task of, given a new data set, try to find a kernel that does a sensible job of separating these two things. And we started off with the RBF kernel, which we see that it doesn't really do a great job of separating things. We can try the SVM kernel as well. And it's sort of better, but like the shape here, like the curvature of this thing doesn't really make a lot of sense to me. So then what we can do is, when the default kernels don't really do the job that we want it to be, is we can try and get a sum or a product of the kernels that we're interested in. So here we were given a function that will return us the sum of two kernels. And we were asked to return the sum of the RBF kernel and the linear kernel, which is just the dot product between x and y. So doing that, and it just takes some time because it's not a very efficient solution. We have, not a very efficient implementation. We have the kernel. We're going to get if it takes much longer, I can just share the solution instead. Yeah, let me just share the screen of the solution because I don't remember how long it took to process initially. There we go. So can you see the render thing? Yeah, cool. So now the combination of the two kernels actually gave me something that seems much more sensible for my data, where in like further away from the data, it behaves somewhat linearly. Like it tries to make a linear boundary of things, but near the data, it sort of tries to accommodate for the fact that there's more points over here of the blue variety, and then like the red points are more dispersed. So yeah, like that's the notebook. It's mostly introductory and gives you the freedom to sort of play around with kernels. So I'm interested whether any of you tried any different kernels and whether you found something to be working better as a combination.
I mainly just ended up trying different levels of polynomials, like this kind of one. I tried to do it with a polynomial degree 20 and then it crashed.
Did you run out of space, or?
Well, I don't know if it crashed. It just took about 5 minutes to do, so I just quit it.
Yeah. So yeah, you can be much more efficient in how you implement the kernels. For example, in the solution, this is a solution file. There is a more efficient implementation of the Gaussian kernel, which actually uses like more. The big thing about the Gaussian kernel, like the big computational cost of the Gaussian kernel, is computing pairwise distances between each of the points in x and points in y. And there are more efficient routines that allow you to do that. And once you do that, the Gaussian kernel becomes much easier to compute. Likewise, with the polynomial kernel, you can be smarter about how you represent that computation. And as you can imagine, the sklearn things have like very efficient implementations underneath. Cool. So that's the SVM notebook. Are there any questions on it? Doesn't seem so. Cool. Right. Let's move on to the next one.
So yeah, I will hand over for the data pre-processing and some dimensionality reduction techniques. Let me share my screen. I think, sorry. Yeah. Okay. Okay, can you see my screen here?
Yes.
Okay, great. Yeah, so that's a very similar process. That the first step is to read the data, right? So we use the Titanic data again to deal with the for this notebook. In this notebook, we will cover some common used techniques for missing value imputation and data transformation rescaling. So these two are very important when you get a raw data set, because your data set might be dirty. There might be some missing value and also some non-numerical variables that you cannot use directly to train and test your machine learning model. So we have to transform them. And sometimes we also apply, no, sometimes, always we apply rescaling for the features. So because you don't want you periodically put some weights or bias to any feature that you have to treat them as equally important, right? So we always apply rescaling to deal with this kind of problem. And I will introduce you some how to this notebook will introduce how to do it, and we will say for detail with some solutions. Okay, so first step is to see the data set. That is a very common. We have seen a lot of times. So okay, that is radius CSV. So we say use a Titanic data set. We want to predict if a passenger will survive, and there are some information given by this data set. And the first step in data processing always we do is to drop some useless features, because you can see if you want to predict if a passenger will survive, the name of the passenger, the ticket number it has, and the passenger ID will not contribute to the prediction results. So we just drop this useless features. You can see it's more tight for the table here. And then we will to detect the missing values within this data set. Let's just run the data set .isNow .sum. You can see some description of that. It shows that for the age feature, it has 177 missing values, and there are also some missing values for cabin and embarked. So the first thing that we want to use is to use a mean strategy. That means I want to impute all the missing value for age feature with mean value of the known ones. So we simply use a simple imputer, which is inserted in contained by the skeleton to impute these missing values by using this code, by running this code here. So let me check. Can we run it directly? It seems okay. It takes some time. Yeah. So you can see here, if we impute all the age missing values of in age feature with a mean, right? By using this imputer, we can check the missing values description again, and then we can see all the missing values in age have been filled. But if we want to verify if that the missing values are substituted by the wanted value, that is the mean of age, which is calculated by here, we can further check the data set later on. Okay, so so here, instead we further want to fill the missing values in Kamen and in bucked. But as we can see here, the Kamen and the embarked features is not a numerical number. So one strategy to deal with this kind of problem, we can use the most frequent value to substitute these things, because we cannot compute the mean values of that. Okay, so here we are going to fill some codes here to see. Well, let me see where is the code that we need to fill in. Is that only this one? Okay, I think you can exactly right. Yeah, we just to check that we also use a simple input, but only change the strategy to most frequent, and we then impute all the missing values with a very similar process like before. And we can see all the missing values are filled now. And we check the data set that all the missing values have been eliminated. We can compare with this one. You can see there are some missing values, for example, here, here, and now they are all fulfilled by the wanted values. And in the scalar, there is also another more advanced method to impute the missing value, but it's accordingly this imputer is still in experimental stage, but we can try to use it. For example, I set a data set by using by manually just set it as any attribute value that you want. For example, we have this data set with the values shown here that we want to impute the numbers, the missing values here. And we can use the iterative imputer with multiple iterations to see which value is the best to fill with it according to the relationship between, for example, the first row and the second row, or the first feature and the second feature. So let's see the results here. As you can see, compared to the original data set, the second feature is always twice of the first. So the iterative imputer also did the same thing for the missing value. Okay, so after dealing with the missing value, we sometimes need to deal with transform the data type. As I mentioned before, sometimes the label or some variables are non-numerical, which cannot be read or understand by the machine. So we need to transform it into some numerical representation. First one is to use the label encoder to encode some, for example, sex feature here to a binary variables, because there is only man, a female and a male. We want to transfer it into, for example, 0 and 1 to represent different class of them. And we simply use the import the label encoder from the scalar processing scalar.preprocessing class, and we use this encoder to encode the data, the sex columns of the data set, and we substitute them, and we can check the results by here. So as you can see, the original here is male, female, male, female, right? So this cannot be used to train our data, our model. So, but if we convert it into this numerical type, we can use it for further potential multiplication. Okay, so however, the label encoder is to transfer data from to the if you have, for example, you have 2 classes here, then it will be 0 and 1. If you have 3 classes, it will be the possible of encoded value would be 0, 1, 2, right? But however, sometimes we don't want this kind of difference, because we don't want to treat the for example, if there has a more type, for example, children, and children is coded to 2, we don't know, when we train the model, we don't want to treat the sample with children with more weights. That we want to have, because you can treat male, female, and children are the same thing. So just for example, of course, children is not a sex, but if you have 3 classes, you have to consider about it. So that the problem is that why we can't encode the male as 1 but female as 0. Because a bigger number may indicate more importance in the model. So we don't want this effect. So sometimes we also use the solution, possible solution is to use one-hot encoding. So how one-hot encoding works is that we want to transfer our classical, we want to transfer our label, for example, 0, 1, 0, and 1 to a matrix, and the number of the columns should equal to the how many classes within the within these features, and we represent it as a Sparris matrix with just like we can show this, and you can see we represent the male by 0, 1, and the female as 1, 0. So that means we use 2D vector to represent that, and this avoids the potential imperial weights that we introduced to this model. Okay, so then further, we if you sometimes we want to also cut for the continuous variables. It's very computation expensive, so we sometimes want to transform them into some discrete values. For example, we can use a histogram to deal with the age one. In this case, we want to have 5 bins for the histogram and put all the age, the age is continuous. We want to put the age feature into different bins, and we can reduce the computation complexity. Okay, we can see here that all the age are converted to only integer number from range from 0 to 4. So now we can also, just a practice, we can also use the one-hot encoding to deal with the age features here. For time limitation, I just can copy the code here, and you can check it later after we publish the solution. So we also exactly follow the same process here. Okay, we show it again. Now the age becomes 5 features, and for example, the first is in the bin 1 will be encoded as 0, 1, 0, 0, 0, and for the age in bin 2, it will be encoded 0, 0, 1, 0, 0, and we encode all the possible values into a unique code here. And then one more thing that always used is rescaling. For the same reason that we don't want to put any feature, which we don't want to treat it more important than others. So we use rescaling to deal with this kind of problem. This is one intuitive example is that if we want to predict a person's gender by using the weights and the height, but if you directly use the, for example, the height measured in centimeters and the weights measured in kilograms, that will introduce bias because the heights always be 160, 150, like something like this, but the weights always a tenth of that. So the model will naturally treat. I think that maybe the height is more important than weight, so we don't want to do that, right? Okay, so here we introduce 2 scalar. One is a standard scalar, and another one is minimum maximum scalar. And the formulas are given here. We do this to push our the distribution of x to a zero mean and with standard variance here by using this operation. Okay. So as you can see, if we operate this on the fair features, we can get the values here. And if we, I think the minimum maximum scalar is more commonly used in practical, because we can scalar all the values within these features to 0 to 1 by operating this formula. So we can implement it the minimum maximum scalar like just exactly like what we operate here. So similarly, I will copy this code here, and you can check it later on. It's very simple, just to change some names here. From sorry, it's a should be this one. Okay, so yeah, it's only change the scalar's name here, and other thing almost the same. And this time we use B class to demonstrate these results. As you can see, where is the results? Oh, here. So all the values here are rearranged to 0 to 1. Okay, that's what we want. We can do this operation for all the features, and all the features will be limited in this range. So finally, we comes to the key part of this notebook, that is the dimensionality reduction techniques. PCA is one of the most popular solution, but not the only one. You can also use such like the linear discrimination analysis and something like this. There are many techniques, but PCA is a very useful and popular one. So we use iris data set here, just like when we used before. We will check the data set again. That's because there are 4 dimensions here, but in fact, you know, we cannot demonstrate a 4-dimensional data in a graph. Only maximum to 3D. Okay, so we simply choose 3 of them for demonstration purpose. So we also use the matplotlib here, and we separate the different class into a different data frame for convenience to plotting. And we plot the 3D diagrams here. As you can see, we choose only 3 dimensions of the original data set, but you can see it can be easily separated by in some way. However, if we want to map it into 2D space with minimal loss of information, how do we do that? We can use a PCA. PCA can map this 3D or high dimensional data into a low dimension by setting a new basis in the space, which has a maximum variance. So according to some information theory things, we can say the data with bigger variance contains more abundant information. So we want to keep this variance as much as possible. So here we use a PCA model with we want to reduce it to 2D, right? And we fit it and just transform the data in 3D, and we can check the results here. So you can say it's also a good mapping into a lower dimension. Maybe it's like you can rotate this 3D map, a 3D plot, and you can say maybe it's just like you mapped in this direction, and to get this one. Okay, so there is also a challenge work that you have to implement your own PCA. logarithm here, but it's only for challenge. The logarithm actually is given by this. You can follow this step by step to deal with it. I'm trying to, it's a little bit time consuming to explain step by step for all of them in coding. So I would like, I may choose it to post it later in the solution and you can check it if you have got a same or very similar results by that. One important clue for that is you have to bear in mind the transpose or the in the whole process, because it will be a little difference between the mathematical formula and the data stored in the Python. Sometimes with and without a transpose will have very big difference. So this is a solution, and you can check it later to compare with the PCA model that you have done by yourself. And let's show the final graph here. You can see it's a little bit different, but in fact it's also it's the same mapping. Only different is that you inverse the axis, but that doesn't matter because the only thing that you want is to keep the information. You want to keep the maximum variance within the basis, and the negative, the opposite direction of the axis that does not affect the performance if you use the data to train your model later on. So yeah, that's all my part, Danny. Hope you can hand over about. Yeah, thank you.
Yep. Thank you very much, Nick. That was a wonderful explanation. Okay, let's then go to new paradigm, clustering. Okay. Now you can see the screen. So clustering. Before the clustering, it was supervised learnings. So we had the labels, we had the answer. So when we train and when we make our loss function or cost function or objective function, we had our labels. So we knew what to do with the new data and we knew how to train it. But in this new example, we don't know the answer. So that's where the clustering comes into play. And the most, I guess the easiest or the famous clustering algorithm would be the K-means clustering. So we're going to look at the K-means clustering. Actually, this YouTube video explains very well. So I'm gonna use this slides to slightly explain the K-means algorithm. All the credits should go to this wonderful man, Alexander. So in the K-means clustering, we have to do 2 steps. So the first step is, of course, setting the loss function, right? As we have been doing in the supervised learning. The loss function here is this one. This is our optimization. The xi is the data points, and mu c is the cluster center point. So the xi will be the like the green dots here, the data points, and the mu c is the red x, the cluster center point. So what we are trying to do is measure the distance between the cluster center and the data points, and we sum up all the distances, and we're trying to minimize that. So from here, if you look at the A, the distance is bigger than B, right? So we are going towards a minimum distance. So that's our first step. For each data, find the closest cluster. So you iterate through all the data points and you calculate the distance between cluster points and the data and you get the sum of the distance. And in the B step, set each cluster to the mean of all assigned data. So if you done with the step A, you know which direction should this cluster point go. This point should go to here, and this point should go to here, because the standard of that is the mean. We calculate the mean of these 2 points and then move the cluster to here. We calculate the mean of these 3 points and move that cluster here to here. This is how k-means clustering works. And then when it stops, then it stops when this cluster points doesn't move at all. Okay. That was it. So this is another wonderful, I don't know, meme. Not the meme, the GIF, the GIF thing. You can see how the process works. Okay, and we are going to do clustering with wine data set. I don't know if you're familiar with wine data set, but this is a very famous data set for clustering because this has a lot of features in it. So in this wine data set, we have 13 features, comprised of alcohol, malic acid, ash, blah, 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 hue, prolin, and I don't know, something that I can pronounce. In X data, we have wine, and in the Y, we have label. But we are not going to use Y, the label here, because we're doing clustering, of course. And then after we do the clustering, we're going to evaluate how we've done the clustering with this Y data. But normally, if you are in the situation where you have to use clustering, since you will not have Y at all, so there should be another evaluation metric for the clustering algorithm. But because we have Y, for the educational purpose, we're gonna evaluate with Y. Okay, so this is the table. We have alcohol to prolin thing, and these features defines the taste or I don't know, something of the wine. And we're trying to cluster these wines based on these 13 features. This is the visualization code that I wrote. Let me explain quite briefly. So this gets X, the input, and this call in X means that if you set 0, 1 tuple in calling X parameter, you're trying to visualize 0th and first column of this table. Of course, this is 2D, and if you want to visualize in 3D, three-dimensional, you can put like 0, 1, and 2. Okay, so if it's 2D, you do this. If it's 3D, you do the following. So here, I set 8, 10, and 12, which means I want to visualize these columns, and this visualized in 3D. And if you do 8 and 10, you visualize in 2D. So as you could see from these data set, imagine you can't just only imagine, but imagine you are visualizing all 13 features in 13-dimensional space. It would be really, really sparse, right? So we do PCA with the sparse data, because if the data is really sparse, it's really hard to set the, I don't know, like borderline, where it's really hard to do any machine learning task in that situation. So we're trying to reduce the sparsity by reducing the dimension, like this, 3D to 2D, or 13-dimensional to 3 or 2-dimensional. So here we run the PCA. You learned with Nick, right? We learned the PCA by doing loading the PCA scikit-learn library and set the number of components, and then fit, and we transform the X into the wanted dimension. So this reduced array will have a two-dimensional data points. And for the distance here, we're going to use Euclidean distance. So it's very easy, right? It's very easy to implement. You just calculate the difference and then square it, and then you do sum, and then you put the square root over the sum. That's the basic Euclidean distance, right? Okay, so in the k-means algorithm, we iterate through all the data points. So here we iterate through all the data points, and we're going to calculate the distance. And also we're going to iterate through the number of clusters. And here it is 3. So yeah, I think you get the point, right? Calculate the distance between xi and the centroids 0, 1, and 2, right? And then you get the minimum distance, and then you set it to the label 0, 1, or 2. If it's change, the change flag will turn into true, and this will be explained in later step, in step 3. This is the break condition, right? And the step 2, you calculate the new centroid based on the new cluster, and then you assign a new centroid in the space by calculating the mean, and then assigning the new centroid k to the xy, the calculated xy. And then if it's not changed, which means this code line is not executed, you break the while loop, right? It's just the implementation of this step. Okay. And then, like Nick said in the previous tutorial, we need to normalize data before we process all the data. Here we're doing a min-max normalization. So you have, let's see, you iterate through all the features, 13 features, and then you look at the first column, and then you subtract the mean. Subtract the minimum, and then divide it by the maximum, so that you can scale it from 0 to 1. That's how you do the normalization here. Subtract mean and divide it by the maximum. And in the main function, we're gonna sum all that up. So we'll first normalize all the column, and then we'll run the PCA, shrink the dimension to 2 dimension, and then we get the shrinked data points. PCA, I'm going to call it PCA X, and I'm going to put this into the k-means algorithm X as an X, and we're going to initialize the central points. Actually, I forgot this step when I was explaining the k-means algorithm. You have to first initialize the centroid points. There are a lot of various initialization method, but here we're just gonna initialize it with 0, 1, and 2. And I'm gonna explain other methods in later. And then we'll set it to 3. I set it to 3 because obviously we have 3 kind of category, 0, 1, and 2. But this is because we know there's 3 category, but if you don't know in a real world situation, there should be also another way to find a optimal k, and I'm gonna tell you later. And then you visualize y, you get this one. So your data is shrink to 2-dimensional, and you divided into the 3 clusters, right? So this was the labels we got from the K-means algorithm. This was our answer, our prediction. And this was the y, which we had in the scikit-learn library. And I'm going to compare these with Hamming distance. You don't usually use Hamming distance maybe in clustering, but I'm going to use it for the comparison. Maybe you can see right here, there's 1, 0, 1 or 1, 2, 1, which seems wrong, right? 1, 2, 1. And if you calculate the Hamming distance, it's 0.05, which means that we got the answer in the ratio of 95%. 95, the 99.5%. Okay, so open questions. This is the maybe most important parts of this notebook. So how can you effectively evaluate your clustering algorithm? I said you can look up the done index. So when you evaluate your clustering algorithm, there are quite a few ways. The first way would be, let's say you have two clusters right here, cluster A and B, and then you can evaluate your clustering algorithm by calculating the distance between two clusters. So if you have cluster A and B, you can calculate the distance between two clusters right here. And the other way is to calculate the diameter of one cluster. So if you have one cluster, and you can calculate the diameter of one cluster. The done index actually use both of it. So if you look at the done index right here, this is the definition. So this can be seen as a grid to you, but this one, this one is this means the distance, the distance between two clusters, I and j. So the first way that I told you, the distance between two clusters, we're trying to minimize the distance between two clusters, and that go over to the nominator, and then this one, the denominator, means that the second method that I told you before, the diameter of the cluster. So here we are trying to maximize the diameter of the cluster, and then this goes to the denominator. So this is the done index, and okay, there's a few more, but this is the I guess the most popular one. The second question: in which situation can K-means algorithm underperform? So you can look up the different clustering algorithm that will explain advantages. Okay, so I actually did some fun thing. If you know what the Monte Carlo simulation, I did something like that and drew smile right here. So imagine you had this data set and you want to cluster this into eyes, mouth, and I don't know, the face structure, the round face. If you use K-means algorithm, you will end up with, I don't know, this is one cluster and this is one cluster and this rest of thing is the one cluster. It won't work. Here you have to use density-based algorithm. So this part is the left eye, and this is really closely densed. So this should be the one cluster. And this whole thing should be the one cluster, and this mouth should be the one cluster. So that's the density-based algorithm. And there are a lot of different clustering methods, like hierarchical clustering and density-based algorithm, K-means. If you go to this one, this clustering in machine learning, it's written by Google, I guess. This has a lot of resources, so you can go check it out after this tutorial. Okay, the rest of the question. is there any way you can effectively initialize initial centroid position? So we, in the code, we initialize with 0, 1, and 2. So that's very inefficient because if we initialize maybe like the cluster points into like here, here, and here, that would be a really inefficient loop, right? So to do it with a good way, this is the 3-way. So the first way is random, what we did. The second way is distance-based. So you first start with the random data point, and then you find the farthest data point from the cluster you've chosen so far. And then you combine these two methods, and you make random plus distance. What this means is that you find, you start with the random data points, but you randomly choose among the farthest points right here. So that's one other way. Maybe I think this is the best way to initialize it. Okay, the last question. Is there any way you can effectively choose K? Like I said before, we knew the K. It was 3 because we had 3 labels, 3 categories. But what if you don't know how many category that you should cluster? In that case, we introduce a new thing, which is the complexity. So this red line here is the error, which is our cost function, the sum of the distances, right? So if you increase K infinitely, you will end up getting 0 cost. Because think about it, if you have 20 data points and you made 20 clusters, that means you have cluster center points right on the data points, which makes the distance 0. So you are guaranteed to the convergence. But the thing is that it is not effective, and the complexity goes up and up as you increase the K. So if we introduce a new term complexity into the cost function and sum those red and green line, we have this blue line, the new thing. And then the lowest point here is maybe 4 or 5K. The K equal to 4 or K equal to 5. So that would be the optimal K. And this is called the elbow method, I guess. Okay, that was all the open questions answered. Do you have any other questions in the notebook or in the open question? Great. Okay, we'll stop share. Okay. This is the end of the tutorial. How was it, guys?
Right. Yeah. The only bit I struggled with in them was the last bit of your one, but you've just clicked it for me now, so I understand them all. It's perfect.
Okay, that's great.